Welcome to 4.4 Introduction to Complex Numbers. Today we are going to simplify complex numbers and solve quadratic equations with complex solutions. So first we're going to have to recall how to simplify radicals. What I like to do is look at my number underneath the radical and see if there are any factors that are perfect squares. If I look at 50, I know that I can rewrite it as 25 times 2. And if you recall from Algebra 1, if I have multiplication under a radical, I can split it into square root of 25 times the square root of 2. This only works for multiplication and division. You cannot do it for addition and subtraction. Well, now I know the square root of 25 is 5. Square root of 2 is a decimal value. This is a non-calculator problem. I'm just going to leave it as square root of 2. My final answer is 5 square roots of 2. For number 2, I'm going to do something similar. If you are not sure if there are perfect square factors, write out a number tree. I wrote mine out for 48. I listed all the factors, broke them down, and I noticed that I had two sets of 2. So I have 4 times 4 times 3. So I'm going to write the inside of my radical as 4 times 4 times 3. This square root of 4 is going to come out, this square root of 4 is going to come out, and it's going to give me 2 times 2 times 2 square roots of 3. And I'm going to multiply these three numbers together to give me 6 square roots of 3 as my final answer. So now that we remember how to simplify radicals, let's go ahead and talk about imaginary numbers. Well, first question, what is an imaginary number? It's a number that is expressed in terms of the square root of a negative number. So previously, if I had a problem like x squared plus 1 equals 0, and I subtracted 1 from both sides, we would stop because when I got to the point where I was taking the square root of both sides, we would say, well, I can't take the square root of a negative number. However, now that we are in complex numbers, we can talk about this in terms of it being imaginary. So the imaginary unit I, which is the variable we're going to use, is defined as I is equal to square root of negative 1. So anytime I see a square root of negative 1, I'm going to replace it with the variable I. So for this problem in particular, I'm going to say square root of x squared is x is equal to plus or minus I as my final answer. Now, the nice thing about this, if I were to come in and take the squared of both sides of the I equals square root of negative 1 equation, I would get I squared is equal to negative 1. So this is another property that we're going to use. Anytime we see I squared, we are going to replace it with negative 1. So let's get to simplifying. For number 3, I'm going to first rewrite negative 25 as factors. Now, my suggestion is always to take out the negative as negative 1. That is what we're going to do every single time. That leaves me with 25, which I know is a perfect square, so I'm not going to touch it. I'm not going to break it down any further. And I'm going to use that property we did previously where if I'm multiplying in a square root, I can take the square root of each value. So 2 times square root of negative 1 times square root of 25. And we've already talked about how the square root of negative 1 is equal to I. So I'm going to get 2 times I times square root of 25 is 5. So I'm going to end up with 10I. You will only multiply the real numbers with the real numbers, the imaginary numbers with the imaginary numbers. And we always write our real number first, and the I we treat just like any other variable. It comes second. For number 4, I'm going to approach it in the same way. I'm going to factor out negative 1 in any perfect squares that I see within 24. So I'm going to leave negative 3i by itself, square root negative 1, because it's a negative number, and 24 I know I can break down into 4 times 6, and 4 is a perfect square. So I'm going to make sure I have that. Now I'm going to pull out what is a perfect square. So negative 3i, and we know that the square root of negative 1 is I. We know that the square root of 4 is 2, and I know that I can't take the square root of 6, so I'm leaving it inside the radical, just like it is here. And now I'm just going to multiply my front terms. So I'm going to do -3 times 2 because that's going to give me -6. And I'm going to do I times I, which treat it just like you would treat x. It's going to become I squared. So -6 I squared square roots of 6. Now you are almost done, but I do want you to remember that we have a rule. If I see I squared, I should be replacing it with -1. So what I'm going to do is I'm going to end up with -6 times -1 square roots of 6. -6 times -1 is +6 square roots of 6 as my final answer. For number 5, I want you to be careful. Anytime you have separate radicals and you have imaginary answers, you have to simplify first before you combine. So let's go ahead and rewrite this as the square root of -1 times 5 times the square root of -1. And I went ahead and broke down 8 into 4 and 2. Because remember, you are always looking for those perfect squares. So I'm going to, for my first term, pull out an I square roots of 5. For my second term, I'm going to pull out an I and I'm going to pull out a 2. So 2I square roots of 2. Now we're going to do some simplification. With radicals, you multiply the first terms times the first terms, and then you multiply the radical inside times the radical inside. So this is going to give me 2I squared, and then the inside is going to be 5 times 2. So I'm going to do a little simplification. Now remember, I squared is going to be equal to -1, so this is going to become -2 square roots of 10. Okay, let's introduce the concept of a complex number. A complex number is written as a plus bi, where a is a real part and b is an imaginary part. So we have addition or subtraction occurring. So let's go ahead and do some simplification with complex numbers. The first thing I have is 2 minus 3i minus 14 minus 7i. I want you to be very careful here, because this negative is going to distribute not only to the 14, but to the -7i. That's going to give me 2 minus 3i minus 14 plus 7i. Now I'm going to combine like terms. You will always combine the real parts with the real parts and the imaginary parts with the imaginary. So 2 minus 14 is going to give me -12, and -3i plus 7i is going to give me 4i. I want to remind you, just treat I as if it were a variable, like a variable x. It's going to get the same rules applied to it. The only thing is, when it's I squared, we just turn it into -1. So this is going to give me -12 plus 4i. You also could write it as 4i minus 12. Both of these are correct. For number 7, I'm going to distribute the 3i to the 2 and to the -7i. So I get 6i minus 21i squared. Now remember, anytime I see I squared, I'm going to write it as -1. So I'm going to get 6i minus 21 times -1, which is going to become 6i plus 21, or you could also write it as 21 plus 6i. You don't have to do both. Just pick one of the ways of writing it. I just want you to see both so you know they're both acceptable answers. For number 8, you also have to be really careful, because you have to remember, if I have addition or subtraction and an exponent, I'm not just distributing. I am foiling. I have to do 2 minus 7i times 2 minus 7i. First, outside, inside, last. It's going to give me 4 minus 14i minus 14i plus 49i squared. Now remember, I'm going to combine like terms, and the i's are just like x's. I cannot combine a single I with an I squared. So the only thing I can do is combine the two middle terms to give me 4 minus 28i plus 49. And remember, I squared is going to become -1. So this is going to simplify to be 4 minus 28i minus 49. Combine the real parts together. So 4 minus 49 is -45. So you could write your answer as -28i minus 45, or -45 minus 28i. Okay, Okay, now that we've practiced some simplification, let's work with some solving problems. For number 9, the first thing I'm going to do is I'm going to subtract 4 from both sides of the equation. Now, you have to kind of decide what the best method for solving is. Now, I notice that I have a squared term by itself on the left-hand side, and I can take the square root of the right-hand side. So I'm just going to solve this using square roots. I'm going to take the square root of both sides of the equation. Remember to have a plus or minus on the number side. And then I'm going to go ahead and simplify my left-hand side. And I'm going to rewrite -4 as -1 times 4. Now remember, I can treat this as square root of -1 times square root of 4. So when I could do that simplification, I'm going to get x equals plus or minus I times 2. Now, normally we always write the number first. So I'm going to go ahead and rewrite this as x equals plus or minus 2I. For number 10, I also noticed that I can take the square root of the left-hand side and I can take the square root of the right-hand side very easily. So that's what I'm going to do. I'm going to square root x minus 7 squared is equal to plus or minus square root of -36. I'm going to go in and simplify the left-hand side to be x minus 7. And I'm going to rewrite the inside of the radical as -1 times 36 because 36 is a perfect square. When I do my simplifying of the radicals, I get I and I get 6. Because remember, square root of -1 is I and square root of 36 is 6. And I'm going to add 7 to both sides of this equation because I want x to be by itself. So I'm going to get x equals 7 plus or minus 6i. And yes, I rewrote this because we should write the 6 in front of the I. So 9 and 10 were easily solved by square roots because it was just one square term and a number value. Anytime you see a term with a single x, you're going to either have to solve by factoring, solve by completing the square, or eventually when we get to quadratic formula, you may have to solve in that way. So I can't do that for this problem, but I'm going to try to see if factoring is an option. Let's go ahead and do our cross. It needs to multiply to be 12 and add to be -6. And I don't have any numbers or factors of 12 that can do that. So I have to complete the square. So what I'm going to do is I'm going to add or subtract 12 from both sides. And then I'm going to notice that A is already 1, so I don't have to do anything to it. But I'm going to identify B as -6, B over 2 as -3, and B over 2 squared as 9. So I'm going to take 9 and add it to both sides of my equation. And when I add it to the side with the x terms, this is going to factor to always be x plus b over 2 and all of that squared. So x minus 3 squared, simplify the right-hand side to be -3. And I'm going to go in and now I can apply solving by square roots. I'm going to take the square root of both sides. And remember, anytime you are on the number side, you have to have plus or minus. And I'm going to go ahead and rewrite the inside as -1 times 3. And know that square root of x minus 3 squared just becomes x minus 3. And I'm going to do some simplification. I'm going to add 3 to both sides. So that gives me x equals 3 plus or minus. Now, if I take the square root of -1, that's going to come out as an I in front. And I can't do anything to square root of 3, so I'm going to leave it alone. Okay, for number 12, we are going to, again, solve by completing the square. So the first thing I'm going to do is I'm going to subtract 54 from both sides of the equation. And I notice that my A is currently equal to 2, and I want it to be equal to 1. So what I'm going to do is I'm going to factor out 2. So it leaves me with x squared minus 6x equal to -54. Once I have made my A equal to 1, I can identify my B. So I'm going to get B is equal to -6, which makes B over 2 equal to -3, B over 2 squared equal to 9. So what I'm going to do is I'm going to add 9 within these parentheses. So be careful because when it's in the parentheses, really what you're adding is 2 times 9 to both sides. So I'm going to add 9 in the parentheses on the left-hand side, but on the right-hand side, I'm going to add 2 times 9. And remember, once I have done my completing the square, it's going to factor to be 2 times x minus 3 squared is equal to -36. So now I'm going to divide both sides by 2. So I'm going to get x minus 3 squared is equal to negative 18. And I'm going to take the square root of both sides of the equation. Remember to have plus or minus on the number side. And I'm going to go ahead and rewrite negative 18 as negative 1 times 9 times 2. Now, with a little bit more simplification, I get x minus 3 is equal to plus or minus 3i. Now that's coming from the square root of negative 1 and the square root of 9. And square root of 2 I can't do anything with, so I'm going to leave it as is. My final step will be to add 3 to both sides of the equation. So what do complex solutions look like? Well, first let's talk about the most typical case. So mostly you're going to see two solutions that are going to be real, and that is where your quadratic is going to cross the x-axis in two places. Our next real option is going to be one real solution where we touch the x-axis and we bounce off of it. This is our double root. It could be concave down, it could be concave up, but you are only touching the x-axis in one place. And our third possibility is having two imaginary or two complex solutions. And this is a quadratic equation, a graph where it is not touching the x-axis at all. This one's going concave up. It could also be concave down as long as it is not crossing the x-axis. So let's go ahead and try to see if we can figure out, is a value a solution to a quadratic equation? These are super easy because all we have to do is take the given value, in this case it's x equals 3i, and plug it in everywhere we see an x in our equation. So what I did was I plugged in 3i everywhere there was an x. So I get 2 times 3i squared plus 4 times 3i is equal to 1. Now be careful with this squared because it's going to distribute. It's going to distribute to the 3 and to the I. That's going to give me 2 times 9 times I squared plus 4 is only going to multiply times the 3. 4 times 3 is 12, I equals 1. Now recall that I squared is always going to be replaced with negative 1. So I'm going to get 18 or negative 18 plus 12i equals 1. Well, you can stop here because you can tell that the left side is never going to equal the right-hand side. This I is never going to become a real number. So because of that, we can say that this is not a solution. We're going to do the same thing for 14. This time it's a little bit different only because I have to plug in 3 plus I. Now you have to be careful again because when there's addition or subtraction within the parentheses and it's being squared, it's not just going to be distribution, it's going to be double distribution. It's going to be foiling, so be careful here. Negative 6 times 3 is negative 18. Negative 6 times I is negative 6i plus 10 equals 0. I'm going to go ahead and FOIL out this first term. That's going to give me 3 times 3 is 9. I get plus 3i, which is plus 6i. And I times I is I squared, which is negative 1. Then I'm going to get negative 18 minus 6i plus 10. And from here, we can do some simplification. Well, first, I'm going to notice that plus 6i and minus 6i are going to cancel each other out. And then I'm going to get, well, 9 minus 1 is 8. 8 plus 10 is 18. And 18 minus 18 is just going to give me 0. So I have 0 equals 0, which means this is going to be a solution. So 3 plus I is a solution to this equation. Now we're going to give an example of a complex number you could subtract from 8 plus 3i that would result in a real number. So basically, I'm trying to find a problem, a value that I can plug in, that I'm subtracting, where I can get no imaginary term. And it has to be complex, so it has to be a plus bi. So you really could plug in multiple things here, but the really, really important thing is that you are getting rid of this 3i. So for my example, I did 2 plus 3i because remember, real terms go with real terms, imaginary terms go with imaginary. So I get 8 minus 2 is going to be 6. And 3i minus 3i cancels each other out. So that eliminates the imaginary piece. That gives me no I. So this was one possible solution you could have. Next, we have Jasmine is arguing with Jade. Jade claims that the product of any two imaginary numbers is a real number. Is Jade correct? Explain. So let's go ahead and approach this in two different ways. First, let's look at the case where I have 2i times 2i. Well, real terms times real terms gives me 4. I times I gives me I squared. And I squared can be replaced with -1. So my answer is -4, which is a real number. So in this case, yes, the product of two imaginary numbers is a real number. But let's look at something else. What if it was 2 plus I? So I have 2 plus I times 2 plus I, and I have to FOIL, so that's going to give me 4 plus 2I plus I squared. I squared gets replaced with -1, which results in 3 plus 2I. Well, for this problem, I have two imaginary numbers that are being multiplied. However, my answer is not a real number. So because of that, we have to say Jade is incorrect. It's untrue because when multiplying imaginary numbers with addition or subtraction results in an imaginary number.